The beach is a spectacular place to observe geologic processes. Moreover, understanding modern beach processes, those that are occurring today, also helps you interpret the geologic record of ancient beaches preserved in sedimentary rocks. I grew up on a barrier island. My folks bought a place, essentially a shack on stilts, when I was a kid, and over the next couple of decades turned it into a year-round place that they would eventually retire to. Living at the beach, you become aware of the rhythms and the changes that occur on a daily, seasonal, and yearly basis. When it was a good time to go fishing, what time was low tide in the bay for clamming or crabbing, when the waves would be big or breaking properly for surfing, and of course, when you had to be careful going in swimming. In the process of enjoying beach activities, the relationship between weather, tides, and ocean conditions became intuitive. As I grew older and started learning geology, I started to understand the influence of weather and tides on the geology of the shore. With my folks living there year-round, I also started to understand how dynamic the beach can be. There's a lot going on at the shore, so let's start with definitions. A beach is an accumulation of sediment found along water's edge. A beach has at least one flat area called a berm. That's where most people in the summertime will put down their blankets, beach chairs, or beach towels, and then relax. Closer to the ocean is the beach face. That's the area that is washed over by waves or tides, and it stays wet most of the time. That's where little kids will splash around and dig for critters. Coastal processes, however, impact an area much larger than just the beach. The term coast is defined as the area from the ocean inland until no ocean-related features are found. The coast includes the shore, where the ocean is in contact with the land, the beach, and any dunes that may have formed. One of the things that makes the coast so dynamic is the interaction of three major geologic processes. Wind-driven processes move onshore sediments and create dunes. Ocean currents move sediment in varying directions, and waves both transport and erode. Each of those three processes, wind, ocean currents, and waves, create their own sedimentary conditions and landforms. Let's talk about waves first. What exactly is a wave? A wave is defined as a surface disturbance of a fluid medium. Of course, the waves you think of are waves at the beach, but you can also get atmospheric waves because air masses are fluids. Disturbances at the interface of a warm and cold air mass are also waves. And you can even get waves forming at the interface between two liquids. There are a lot of stories of submarines encountering waves at the interface of colder or saltier, which are denser waters, with warmer or less salty waters, which are less dense. During World War II, submarines would run silent while traveling through the Strait of Gibraltar. The saltier Mediterranean water would flow into the Atlantic Ocean at depth, and warm Atlantic waters would replace it as surface flows. Where the two waters met at depth, or the interface, dangerous waves for a silent submarine would frequently form. Ocean waves form at the interface between water and the atmosphere. The size of the waves is a function of three things: the velocity of the wind passing over the water, the distance the wind is blown over the ocean, called a fetch, and the duration of time that the wind blows in a particular direction. Waves are bigger the longer the wind blows, the faster the wind blows, and the longer the distance that the wind has been in contact with the ocean. Every time the wind changes directions, the process starts anew. There is also a maximum size the wind-generated waves can reach. Waves are described by their height and wavelength. Wave height is the distance between the trough and the crest. Wave length is the distance from the crest to the crest. The time it takes for one wavelength to pass a given point is called the wave period. Ocean waves can travel essentially around the globe if they are generated by enough energy. This is because the water that makes up the wave is not what moves the entire distance. Rather, a wave is the propagation of energy through a circular motion of the water. Most people have run across this. You put a cork or float of some kind on the surface of the ocean. The float will move up and down with very little forward movement. What's happening is the water directly beneath the float is moving in a circular pattern. At a certain depth, a depth that is approximately half the distance of the wavelength, water movement is negligible. This motion of water within a wave is really the key to understanding beach processes. When people think of waves, invariably they think of the waves that break with a tube. That is, the waves surfers seek out. Those are called plunging breakers, where the crest of the wave curls over and breaks with a single crash. But plunging breakers are just one of 4 types of waves. In addition to plunging breakers, there are spilling breakers, which break gradually over a long distance, collapsing breakers, where the crest does not break, but the lower part steepens and then falls, resulting in turbulent water, and surging breakers, which surge up the beach with only minor breaking. It turns out that geology can influence wave formation. Conversely, identifying types of waves helps you begin to understand the geology of the ocean floor just offshore the beach. In particular, waves and the way they break are affected by the geological shape of the ocean floor. Beaches that have a very gentle slope typically have spilling breakers, depending on wind conditions. Gentle beach slopes are common throughout most of the U.S. East Coast and the Gulf Coast. The reason is that the North American plate is rotating due to plate tectonics in a counterclockwise direction. The trailing margin of a plate is absent of tectonic activity, no subduction, for example. The result is a big continental shelf that extends well offshore and an ocean floor that gradually drops off from the shoreline. As waves approach the shore, friction slowly begins to slow down the bottom portion of a wave. So when you envision the rotation of water particles in a single wave, the circular motion at the bottom portion is slowed down by friction. The water in the wave then begins to move in a more elliptical pattern. When this occurs, the base of the wave begins to slow down. In the case of spilling breakers, the process of slowing down the wave is gradual. As the water gets shallower, the entire wave will slow down due to friction. But the base of the wave slows more than the crest. The crest of the wave will rise, and because the following wave has not slowed down as much, the wavelength will decrease. If this process continues to occur gradually, eventually the crest will topple over, gradually turning into white water, and the white water will roll forward. This is a spilling breaker. The plunging breakers occur for the most part where the wave approaches the shore in deep water, resulting in minimal impact of friction. When the wave is very close to a reef or the near shore, the shape of the wave and the height of the wave crest will change quickly. The result is that the top of the wave becomes unstable. This results in a classic tube or barrel that a surfer seeks out. All of us who grew up on the East Coast were doomed to an adolescence of surfing spilling breakers. Our only hope for plunging breakers and good tubes was a strong offshore breeze. When the wind blows off the land towards the ocean, it can effectively hold up the crest of the wave. It was a common occurrence in my neighborhood for kids to report that the offshore breezes were holding up the waves and it was time to go surfing. Many times, the offshore breezes were generated in association with storms out at sea. On those days, not only were there well-forming plunging breakers, but they were big too. Conversely, onshore winds favor waves to have spilling breakers. On the west coast of the United States, you have plate tectonics making what's called a leading edge. Here, the North American plate has hardly any continental shelf at all. Instead, very close by, there's the Pacific Plate, with the North American plate sliding in a south-southwest direction toward the Pacific Ocean. Without a gradually rising continental shelf, wave energy is not dissipated until you get close to shore. Under the right conditions, you can have some spectacular plunging breakers. The same is true on islands or places surrounded by coral reefs. Hawaii is a great example. The waves out at sea are deep water waves, and they are not affected by friction at the wave base. Under these conditions, the waves approach shore, then quickly steepen and collapse as plunging breakers. There is an inherent danger with plunging breakers. The water shallows quickly, resulting in a well-formed tube, but because the water is shallow, a surfer or a swimmer can be driven into the substrate. Falling off of a surfboard or being driven by the wave into a coral reef can be a very dangerous situation. A collapsing breaker is somewhere in between a plunging breaker and a spilling breaker. The wall of the wave is steep, but the crest still rolls over and creates white water. The surging breaker forms where small waves meet a steep shore. The advancing wave ends up pushing forward into the return flow of the previous wave, creating a complex interaction of water motion. The energy of waves can result in very dynamic geologic processes. As a wave approaches the shore, sedimentary particles are moving in several directions. The circular motion of water in waves will pick up sediment and move it towards the beach. After the wave washes up against the shoreline, it will then transport sediment from the beach back out to sea. This zone between the beach and the breaker line is called the surf bore and the swash bore. I have a sample of sandstone that's 300 million years old, and it records the motion of sediment landward and seaward. What results is the formation of a surface that has symmetrical ripples. They're preserved in ancient sedimentary rocks, and you can see them easily on a modern shore. The current goes back and forth, and the ripples you see are symmetrical. But for the most part, sediment is suspended in the water column. If you've ever tumbled over after being hit by a wave, in addition to being a little bit disoriented, you find yourself with a bathing suit full of sand. That is suspended sediment of the surf bore and swash bore. The largest sedimentary particles, although they aren't usually much larger than the beach sediments, will be found right where the waves break. This is called the breaker line. Those large sediments tend to stay right around the breaker line. They're usually too big to be either transported either landward or seaward, but they will end up being transported parallel to shore. What happens over time is that the lateral movement of sand builds up into a sandbar. Sandbars create a feedback mechanism. Right at the sandbar, the substrate shallows. This results in the breaking of a wave and the deposition of fairly large particles. This depositional process results in the stabilization of the sandbar. So when you go to the ocean, you'll frequently see waves breaking offshore in about the same place as the sandbar. Of course, it's not like a sandbar is a permanent feature. All that has to happen is for a storm to come and move the sand particles that couldn't be moved under more ordinary conditions. One thing I have to mention here is the relationship between sandbars and rip currents. If conditions are right, storms or large waves will create a discontinuous sandbar, that is, a sandbar with a gap in it. When this happens, you have waves breaking on the sandbar, but no waves breaking where there is a gap in the sandbar. This gap in the sandbar can create a rip current. After wave water washes up onto the beach, it will then flow back towards the ocean. The gap in the sandbar creates a natural path for the seawater flowing outward. This is a rip current. Rip currents can be very dangerous, so this is one of those times when understanding geology can save your life. So let's talk about currents, the second important coastal process. Currents are formed because waves do meet the shore at a slight angle and then move back towards the sea at a different angle. This in and out dynamic in what is called the swash zone results in movement of sediment parallel to the beach. The process is called longshore drift. The sediment that is moved is called the river of sand. If the transport of grains is unimpeded, longshore drift will generate incredibly interesting geologic features, like bars that block part of a waterway, spits that extend out into the sea and curl around, and a sandy kind of isthmus called tambolos. Some of these landforms are spectacular. Frequently, people build structures to impede the movement of longshore currents. This is an attempt to manipulate the river of sand and build a bigger beach. This always causes trouble. Structures like jetties or groins essentially slow down longshore currents. Just like any flowing water, when the water slows down, a portion of the sediment that it's carrying will be deposited. A decrease in transport energy results in deposition. So the construction of a groin slows the longshore current down, sediment gets deposited up against the groin, and you have a bigger beach. What's not to like? The problem is that on the other side of the groin, longshore drift will begin again. On the downdrift side of the groin, longshore drift will erode the beach to pick up sediment. And once a single groin gets built, all the other people downflow of the longshore current have to construct a groin to make sure that they have beach. In certain conditions, it is just embarrassing to see the concentration of structures all designed to build up a beach in front of a particular property, all of which resulted in beach erosion in the next property downflow. In the end, you really don't know how effective the process is. In the 1960s and 1970s, 3 groins were constructed in front of the Cape Hatteras Lighthouse in an effort to preserve the historic structure. It was built in 1870. The result was that the beach got larger, but the dunes below the lighthouse got flatter. The sand had to come from somewhere. Finally, in 1999, the lighthouse was actually moved to safety further inland on the barrier island. The last of the 3 dominant sedimentary processes at the coast is wind. Wind creates dunes that on some coasts are spectacular. Coastal dunes form as a result of the availability of sand and the presence of strong landward winds. Why is that? Ocean wave action provides the sediment, and the contrast between ocean temperatures and land temperatures provides the wind. What can result is the construction of a series of what are called foredunes forming parallel to the coast. The Indiana Dunes parallel to the shoreline of Lake Michigan are a good example. North Carolina's dunes on its barrier beaches are another good example. The sediment of coastal foredunes is really interesting. Because foredunes are constructed by prevailing winds, they have a very consistent grain size. The sediment that makes up the foredune will be a little bit finer grained than what makes up the beach, and there will be less variation in the grain size. If you get a reasonable exposure, you can see that dunes are made up of spectacular, steeply dipping strata called crossbeds. Sand grains, as they are pushed by the wind, work their way up the slope of the dune. And when they reach the dune crest, suddenly they're protected from the wind that was moving them. The result is that they cascade down the downwind side of the crest. That's what creates these crossbeds, which characteristically form at about 32-degree angle. It's the angle of repose. It's the combination of this steep slope and the presence of well-sorted, fine-grained sand that invite all kinds of activities on beach dunes. On the barrier beach near Kill Devil Hills, North Carolina, the dunes called out to the Wright brothers. The combination of strong winds and the possibility of a soft landing in case of a mishap made those dunes the perfect place to launch their flyer. People are still heading there to take flight. You can hang glide down the slopes of dunes like Jockey's Ridge without fear of a hard landing. Even on foot, the soft sand and angle of the repose of the coastal dune can inspire a headlong leap downslope. But when walking or running down any loose slope, you have to make an extra effort to keep your feet underneath your body and your head back. If your head gets in front of your feet or your feet get bogged down, you're going to take a tumble. A particularly radical faceplant by my kids on the slope of Jockey's Ridge is one of their strongest memories of our family vacation at Kitty Hawk. So where does all the sand come from? Why is a beach sandy? The important thing to remember is that coastal processes we talk about tend to keep sediment either on the beach and dunes or in the near shore. Certainly, during high energy events, sediment in the nearshore and coastal environment can be transported away. But for the most part, the particles are deposited and eroded and then redeposited again. So once material is in the coastal system, it stays there. So how does it get there? The materials that make up a beach come from the land nearby. Rivers will bring sediment to the coast and deposit that sediment in a delta. Once the river sediment is in the ocean, then coastal processes will deliver those sediments to the shore. Wave action will also erode any rock that makes up the coast, and a portion of the eroded material will remain nearby. So beaches are made up of the particulate matter derived by either wave erosion or river deposition. That means that a beach will be made up of those materials available to it. White sand beaches up and down the east coast of the U.S. predominantly consist of quartz grains. Quartz comes from granite, the rock material that makes up most of the continental landmass. The mineral composition of granite is feldspar, quartz, and to a lesser extent, minerals that are made out of iron and magnesium. Quartz is the hardest of these minerals, so as the rock materials are broken down by wave and current action, quartz will persist. Newly formed beaches will have a blend of quartz, feldspar, and rock particles. But the longer the sediment stays in the nearshore system, the more the quartz will come to dominate the particles on the beach. So here is a quartz beach sand from a barrier beach in Texas. But beaches that form in places that don't have quartz or other components of granite will be made up of whatever materials are available. These beaches, of course, come in all colors. The black sand beaches of Hawaii or Iceland are black because they are made up of broken up basaltic lava. Pink sand beaches of Bermuda are that color because they are made up of broken up pieces of pink coral. One of the oddest beaches I've been to is the green sand beach on the big island of Hawaii. This is a small beach made up of broken up olivine. I'll warn you, it's a long walk to get to it, and you'd have to bring a lot of water if it's warm out. But when you arrive, you're inside what was once a cinder cone volcano, while facing the ocean where the volcano originally had an east side. It's a really interesting place. Because of the economic importance of beaches, the tourist industry that revolves around visiting beaches and beach activities is a billion-dollar industry. The presence or absence of sand at a beach, called the sediment budget, is a great concern. The sediment budget of a beach describes how sand arrives at the beach and how it goes away. As I mentioned, for the most part, beaches are fairly stable. But with storms, human activity, and changing coastal conditions, some beaches experience the loss of sediment. Sand arrives to the beach by longshore currents, coastal erosion, and rivers. Sand is removed from the beach by that same longshore current, wind transport of sand to the dunes, rip current transport, and the big one, backflow from a storm surge. Most of the sand that leaves the beach doesn't go very far offshore. If you think about it, waves can only move sand that interacts with the circular motion of the wave water. In water that's deeper than that, there's little sediment transport going on. But regardless of how close the sand is to the shore, a depleted beach is still a depleted beach, and beachgoers will be unhappy. To replenish a beach, communities are forced to dredge sediment from one place and pump it close enough to the shore so that wave action and longshore drift will ultimately deposit it on the beach. Under best case scenarios, you take sand that was once beach sand but has been transported offshore and you pump it back towards the land. But if there is not a good source of sand close by, some communities have to resort to dredging sediment that is not part of the beach system. The result is that the sand that is dredged doesn't have the same characteristics as the beach sand. The dredged material is not mostly quartz. It's not a consistent grain size. It's not the rounded sand grains that occur on the beach. In some cases, the material used to replenish a beach might have organic components or particulate matter consisting of plastics or construction materials. It certainly lessens the beach-going experience. The replenishment of beaches has to be carefully planned. But still, all in all, you're dealing with geologic processes, and beaches are going to erode. At a certain point, depending on conditions, a community may simply give up on beach replenishment. Barrier islands are long and narrow ridges of land that form parallel to the coast. They form on gently sloping, sandy shorelines, and they make up a little over 10% of the world's coastline. In the U.S., along the Atlantic coastline in the Gulf of Mexico, there are about 400 barrier islands. Some of these have been heavily developed and include some of the most valuable real estate in the country. Places like Atlantic City, New Jersey, or Galveston, Texas, are barrier islands that attract millions of people to the coast each year. A typical barrier beach has a coastline, a beach and dune complex, a lagoon, and tidal inlets on either end. The sedimentary environments that make up the barrier island systems are influenced by coastal processes, inflow from the mainland, sediment deposition in the lagoon system, and storm sedimentation. Barrier islands tend to form near river deltas and in areas with relatively flat coastal terrain and low tectonic activity. They are also associated with post-glaciation rising sea level and strong storms. Thus, barrier islands are relatively unique geologic phenomena. And since sea level is still rising, they are, to a degree, ephemeral. Rising seas will eventually submerge them. But that will take time. The more immediate concern for barrier islands is the creation of inlets. Historical records that have been kept about barrier islands, for example, the barrier islands off of Long Island, New York, show that inlets cut through barrier islands during storm events, like hurricanes. When a new inlet forms, longshore currents will fill in older ones. It is a process that is slow in terms of human timelines, but it is continuous. Now, my concern isn't the infilling of existing inlets. Engineers and coastal planners will ensure that existing inlets are dredged and maintained to keep them open. My concern is the creation of new inlets. This happened in Florida in September 2020. Hurricane Sally created 2 new inlets in a barrier beach. Luckily, that particular area was undeveloped. When hurricanes strike barrier islands, many times erosive forces are focused on a relatively small area. Because of waves, the generation of strong currents, and a storm surge, hurricane erosion can result in a barrier island being breached. It is impossible to predict where a new inlet will form or under what conditions. If there is a structure in the location that a new inlet is forming, the structure will be destroyed. That's why there's such a great concern when hurricanes strike barrier islands. The National Oceanographic and Atmospheric Administration do a very good job of tracking and predicting hurricane paths, but no one can predict where the most erosion will occur. Please heed warnings and stay safe. Rachel Carson, a favorite author of mine, once wrote, "To stand at the edge of the sea, to sense the ebb and the flow of the tides, to feel the breath of a mist moving over a great salt marsh, to watch the flight of shorebirds that have swept up and down the surf lines of the continents for untold thousands of years. To see the running of old eels and the young shad to the sea is to have knowledge of things that are as nearly eternal as any earthly life can be. Visit the beach with a geologist's eyes and see the eternal processes of a coastline. Both on modern coasts and in the rock record, you can see the dynamic interaction of waves, ocean currents, and winds, leading to a constant interfingering of sediments and blending of landforms. In the next lecture, we'll talk about how coastlines of the past are preserved in the geologic record.